Welcome back to ECE 340. Today what I want to discuss is filter design, and that's coming to us from section 10 in chapter 4. The first thing that we will talk about is the qualitative idea or concept behind poles, and where do we locate those poles in a low-pass transfer function, or in a low-pass filter transfer function. And then we will look at a particular pattern, which is a Butterworth pole pattern, and that actually provides us with a maximally flat magnitude response. And we'll work through an example, that being a third-order low-pass filter. We'll start by looking at all of these Butterworth pole patterns normalized to a frequency of omega naught equal to 1 radian per second. Then we will talk about how we can change that generic or normalized frequency of 1 radian per second to any bandwidth we want, and that's what we will then talk about in frequency scaling of transfer functions. Where we can go from that point then is quite far in terms of what you already know how to do. We can move into chapter 10 material where we can take the transfer function, we can create an all-integrator block diagram. That then will be a collection of integrators, gain blocks, and summing junctions. Those particular pieces can now be realized with op-amp-based circuitry, and in that sense you could picture a given filter, or how you would realize what's the realization of that filter that you created a transfer function for. Once we have it in the all-integrator block diagram, it's straightforward to find a state space representation. That's simply assigning the outputs of your integrators as your state variables. Now we have a state space representation of a low-pass filter. That's chapter 10 type material, and that's really continuous time material or description of the system. We can approximate that and create a discrete time filter. And by doing that, if we discretize the filter, we can now take the Z transform of that system of equations. That will now provide us with the opportunity to go from state space to transfer function. Once we have a transfer function in the discrete time setting, we can do similar analysis techniques that we've done before, or manipulation techniques, and create a difference equation. Once we have a difference equation, we can now produce an all delay block diagram. And from that all delay block diagram, you can now think of how you might realize or recursively implement a filter. And if somebody now gives you a collection of points or data, and they say, here's a noisy collection of measurements that I have, and I need you to low pass filter these measurements. Now you could actually do that without necessarily going into the lab, unless you consider your desk the lab. You could then create this recursive discrete time approximation of the filters that we're designing. That could be of any order that you want to meet the design specifications that you're looking for. And you could number crunch that data set that you were given and do the low pass filtering numerically with this discrete time implementation or realization. Meaning we now have the ability to do a lot. And chapter 5 we won't explicitly be covering per se, but I wanted you to realize that with the material that you now possess, you have the ability to work with a lot of different representations of circuit concepts, or even in more general cases, system concepts. Let's now start with this idea of filters, and in particular, if we're going to be selecting poles and zeros, How is that actually accomplished? How do we actually create these filters out of selecting pole locations and zero locations? Let's first try to see if we can obtain a qualitative behavior behind this process of selecting poles and zeros. To do that, let's concentrate on how the poles work. Now, if you get nothing more out of this lecture, what I do want you to take home is that poles provide gain enhancement. They enhance the gain based on where you put those poles, and where you put those is related to their frequency. And that's what I want to talk about today. Before we get into a specific low-pass filter, let's remind ourselves of where we've been and what you already know. Suppose that somebody provides you with the following transfer function. They say, here's a system, h of s, has a finite zero at s equal to -1, and let's say that it has now two poles, one at -2 and one at -3. And I would like you to start thinking about different ways of visualizing or conceptualizing or developing an intuition into what that transfer function is doing. One way you can do that is to think about that transfer function as a collection of poles and zeros in the complex S-plane. We just said where those were located. We said that we had a 0 at -1, and we had a pole at -2 and another pole at -3. Now, one way to start to think about what's happening with that particular transfer function, capital H of S, is to ask the question, what would happen if we excited that system or we drove that system with a sinusoidal waveform? In particular, what if we used x of t as the input, where x of t now has a frequency of omega equal to 0.5 radians per second? What's going to happen now at the output? Or more specifically, what happens in the sinusoidal steady state? You could ask the question, well, how long are we going to have to wait in time until we reach the steady state response? And how would you answer that question? What actually influences the transient? The transient is impacted by your poles, and you know where those are at. They're at -2 and -3. And the time constants associated with those poles are reciprocally related to the pole locations, meaning the pole at s equal to -2 actually is going to give you a mode that looks like e to the -2t, and you could now say, well, I'm interested now in the time constant associated with that. When the exponential term, the 2t, what's the value of time when that equals 1? And that will give you the value of one time constant for that particular pole. And in that case, we have a time constant of 1/2 with the pole at -2. With the pole at -3, we now have a mode in our response, the total response, that has a characteristic shape of e to the -3t. We could now say that its time constant is such that the exponent 3t, which will replace t with tau and say 3 tau sub 2 equals 1, that occurs when tau sub 2 is equal to 1/3. For our particular case, the transient is going to be dominated by the slowest pole, or the time constant that's the longest. In this case, tau 1 is the longest, and we would have to wait 5 of those longest time constants, roughly, until we reach steady state. In this case, if we wait tau sub 1, 5 of those, we now are waiting 1 second before we reach steady state, or sinusoidal steady state. Once we've reached sinusoidal steady state, which doesn't take very long, it takes a second, what's the behavior of that response? And that also we can obtain insight from by looking at the pole zero diagram. If we're interested in the sinusoidal steady state, what we're really asking is, how does this system behave as we walk up the imaginary axis? Here's our imaginary axis, here's our real axis, and when we get to the value of frequency of 0.5 radians per second, that's where we are underneath this big top circus tent, and we can now look at how these different pole and zero factors contribute to the overall response of that system. And we can now have a length to that point, J 0.5, from the 0, and we have the two lengths from -2 and -3. We'll take those ratios, and that will now give us the magnitude of our system at 0.5 radians per second. We can also find the angles that those poles and zeros make or produce at that particular frequency of J 0.5. We can take the angles of our zeros, which in this case is 1 angle, and we can subtract all of our pole angles, and that will now give us the phase, or the angle, of our system H, capital H, at J 0.5. Taking those two pieces of information, we know that we now start with a magnitude of 4. That was the magnitude of our original input, x of t. We scale that by what the system does at the frequency that the system is being excited at, which is 0.5 radians per second. And now we take the magnitude of that transfer function at that frequency. We will maintain that cosine, or that sinusoidal behavior, at the input frequency. This is a linear system. We're not going to change the frequency. If we're shaking this system at 0.5 radians per second, we're going to see that everywhere in the system, and because of that, we're going to see it at the output. And then that argument of the cosine will be modified by the phase of our system, and that again is this combination of zero angles and pole angles, where we add up the zero angles and subtract the pole angles, and that will be then our sinusoidal steady state response. That's now how the system of poles and zeros impact the relationship between an input excitation and the output response y of t. Let's now look at the case where we just look at one pole factor. That previous example looked at a 1, 0, and 2 poles, and maybe it wasn't clear what the poles were actually doing or how they contributed to the behavior of that output response. Let's now assume one pole at a value of frequency S naught of -a plus j omega naught. This now is making the assumption that we only have one complex pole. Obviously, if we're dealing with real transfer functions, we want to have our poles and zeros occurring or being in complex conjugate pairs, but for now the concept is easy enough to talk about, or maybe more cleanly talked about, when we just restrict ourselves to one complex pole and don't worry about its twin or cousin below it or its conjugate, which would be at A minus J omega naught. Here is our pole at S naught equal to minus A plus J omega naught. What we want to do is understand how that pole influences the magnitude of the system as we adjust the frequency of our system. Let's now look at a given frequency, omega, and now we're going to move that frequency omega from DC, or the origin, all the way up to infinity. And when we want to ask, how does the frequency response, the magnitude of our system, how does that vary as we adjust omega relative to where that pole is? That pole is now at minus A plus J omega naught. Here is our transfer function of the system. We have this H of S. We are assuming that we only have the one complex pole, and that's now going to be at S minus the pole location, and we now have S minus a minus A. We now have S plus A minus the J omega naught. That's the transfer function as a function of the Laplace transform variable S. What we really are interested in is the frequency response, which we can obtain by replacing S with J omega, and we now have the frequency response as K over J omega plus A minus J omega naught. That's now the expression for our frequency response. And this now provides us with a complex number, and if we find the magnitude of that complex number, that's how the signal at a frequency omega will be adjusted at that frequency, its magnitude. And if we looked at the phase of this complex number, that would provide us with the way that the phase is changed as the signal x of t is processed by the system. Let's now look at the magnitude of h of j omega. We want to know what's going to happen as we adjust omega from DC all the way up to infinity. K we're assuming is positive. The magnitude of that we can just say is K, where we're saying that the magnitude of this quotient is the quotient of the magnitudes, and the magnitude of K, where K is positive, is just K, and now we have the magnitude divided. We'll divide that K by the magnitude of the denominator, which is the magnitude of J omega plus A minus J omega naught. And what is that? Well, that's actually, if we go back to our diagram in the complex S-plane, we will see that that magnitude we can write as the distance from the pole to the point on the imaginary axis in question, the J omega location. Look at what we have. We now have, we want to find the magnitude or the length of this complex denominator value. And that is now made up of three pieces. It's made up of J omega, it's made up of a real part, and then it's made up of minus J omega. If we go back to our picture in the complex S domain, we can say, well, we can actually see what that L, lowercase l of omega, is. It's actually going to be this distance from the pole to the frequency in question. This is now our L sub p, and it's a function of omega. We're adjusting that omega from the origin, or DC, all the way up to positive infinity, and we want to ask the question, what does little l sub p look like as a value? We can better understand that if we look at what we have. We have j omega plus a minus j omega. Let's now just walk over a distance a. Then we can walk down a distance of minus j omega naught, and then we finally go back up an amount j omega, and that puts us in terms of distance from the pole at the same distance as little l sub p. We've now walked a real distance a to the right. We've walked down minus j omega naught, and then we come back to the frequency in question, j omega, and that now gets us to the point on the imaginary axis where we want to find the distance of that value, and that's just the hypotenuse of this right triangle made up of a and the difference in the imaginary pieces between omega and omega naught. What I want you to start thinking about now is what happens as we adjust omega from DC all the way up to infinity. We are going to now look at what would happen to L when it's down here at DC, and then what's going to happen to L when we bring it up to here. And then we're going to just start bringing it further and further up the imaginary axis, and we want to know, how does that length, L sub